Welcome, fellow chemists, to the first video in a series on substitution and elimination reactions. I've done numerous videos on electrophilic addition, and my most recent organic chemistry video covered radical substitution. Today, let's journey into the world of nucleophilic substitution, specifically with alkyl halides. There are two mechanisms for these reactions known as SN1 and SN2. In one of them, the nucleophile approaches the molecule and replaces the halogen in one step. In the other, the bond between the carbon and halogen breaks spontaneously, forming a carbocation. Then the nucleophile reacts with the carbocation to form the product. You're probably thinking, finally, chemists are being reasonable and called the one-step process SN1 and the two-step process SN2. Your first mistake was assuming chemists were reasonable. Chemists decided that the one-step process deserved the abbreviation SN2, but why? To understand where it comes from, let's break it down. S is for substitution. No surprise, as I said, this video covered substitution. N is for nucleophilic. No surprise again, as I said, this substitution was nucleophilic. 2 is not for the number of steps in the reaction, though. Instead, it means bimolecular. You may think, okay, chemists, I get you. You picked 2 because there was one alkyl halide and one nucleophile, and 1 plus 1 equals 2. Yeah, it's not that either. The use of the number 2 indicates that both the halide and nucleophile are involved in the rate-determining step of the overall reaction. In other words, the rate of the reaction depends on the concentration of both species. That's probably as convoluted a reasoning possible for the use of the number 2 when there was a much simpler one available. Luckily, we can rely on product formation rate knowledge involving tertiary, secondary, primary, and methyl structures, except of course we can't here because it's a completely different story. The reason why is partially due to the fact that in order for the reaction to occur, the nucleophile needs to encounter the alkyl halide, specifically the carbon atom to which the halogen is bonded. For the reaction to take place, the best location for the nucleophile to find is the side of the carbon atom opposite the halogen. This is called a backside attack, and in order for this to happen, the nucleophile not only needs to come from the right direction, it also needs to get close enough to the carbon atom itself. It's possible that the nucleophile encounters something that prevents, or at least slows down, the reaction from occurring. This is known as steric hindrance, and I must admit it's tough to visualize when looking at 2D structures like this, so I will replace each of them with a 3D electron potential map. Starting with the tertiary halide, we can see there is a small blue area opposite the halogen which the nucleophile must find in order for a reaction to occur. If you're thinking that's really small, you're correct. We say the steric hindrance is high and therefore chance of reaction is low. On the secondary halide, that blue area is a bit bigger, meaning the nucleophile has more space to attack. It's less sterically hindered and therefore more likely to react than the tertiary halide. There is even more space for a nucleophile to find on a primary halide, so it is more likely to react than either tertiary or secondary. Finally, the methyl halide has the most space of all. We would say this molecule is unhindered, and it is why the product formation rate is the highest. Now that we know which halides are more likely to react and why, we can move to the mechanism of the SN2 reaction. For our purposes, the mechanism is surprisingly simple. If the nucleophile can reach the carbon, the bond between them forms while the bond between the carbon and halogen breaks. At this point, we don't have the original reactants or isolated products. We have reached what is known as the transition state. We get the products as the new bond fully forms and the old one breaks completely. Because I pause the reaction in the middle, you might think this is a multi-step process with an intermediate. However, as you can see as I replay it, this is a one-step process with no intermediates. Now that we have seen the mechanism and we know that steric hindrance is also a thing, let me test your knowledge with a simple question. Which of the following statements is true? Pause the video and think about it. Perhaps even build the molecules at moleview.org. You might think that since ethyl bromide is a primary halide and propyl bromide is too, that their reactivities are more or less equal. As we saw earlier, more alkyl groups resulted in greater steric hindrance. Though technically there is only one alkyl group bonded to the carbon the nucleophile will attack, the groups are not identical, and so the reactivity is not equal. The ethyl bromide has a smaller alkyl chain, and we can see the blue area where the nucleophile needs to attack for a successful reaction to occur. Propyl bromide has a larger chain, and the blue area has reduced in size. This indicates it's more hindered than ethyl bromide. The difference may be subtle, but it is enough for us to conclude that ethyl bromide is more reactive than propyl bromide. If subtle differences in structure can have a big impact on the outcome of SN2 reactions, let's take a closer look at them. For this video at least, those subtle differences I'm referring to are isomers. I've talked about cis-trans and EZ types before, but I need to introduce another one, stereoisomers, which go by the designations R or S. They deserve a video of their own, and if I ever get around to it, a link will pop up now. Knowledge of these isomers allows me to make the following claim. If the configuration of the reactant is known, then the configuration of the product can be determined. For example, if S2-bromobutane reacts with a hydroxide ion, one of three things can occur. After substitution, the product can be all S-butanol, all R-butanol, or a mixture which we could call butanol for simplicity. If you're looking at the screen thinking to yourself that both structures are identical and that R and S is part of some elaborate ruse, it's a good thought, a very good one indeed. But rest assured, I'm not messing with you here. I won't give you the answer just yet, as I will first do a quick refresher about RS configurations with respect to S2-bromobutane. Before starting, I'm more interested in how we can answer the question posed earlier, so I intend on saving much of the stereochemical nuance for another video. Now the first thing we need to do is identify an asymmetric carbon, which is one bonded to 4 different groups. We see the second carbon from the right is bonded to bromine on top, ethyl on the left, methyl on the right, and hydrogen on the bottom. We can now determine the configuration as R or S. To do that, we label each group with a priority value using the same considerations as we did for easy isomers. Of the atoms this carbon bonds to, bromine has the greatest priority because it has the highest atomic number. In the clockwise and anti-clockwise directions there are carbons, so the tie needs to be broken. Clockwise, the carbon is bonded to 3 hydrogens, but anti-clockwise, the carbon is bonded to 2 hydrogens and another carbon. This breaks the tie and gives the priority after bromine to the ethyl group. Completing the table, methyl is third and the hydrogen fourth. Since the ethyl group is to the left or anti-clockwise direction, we can identify this as the S isomer. If I make the mirror image of this molecule, bromine retains the highest priority, but we see that the ethyl group is located to the right or clockwise direction. This molecule gets the configuration R. Now that we have some idea of how to label the isomers, let's look again at what happens when the nucleophile comes along. So here's a structural representation of 2-bromobutane. Bromine is represented by the orange circle, the ethyl group in teal, methyl with maroon, and hydrogen in the white circle in the back. This is the S isomer because the priority around the second carbon goes to the left. The nucleophile ready to attack is the hydroxide ion. The nucleophile attacks the backside, which is 180 degrees from the bromine atom. As it approaches, it will push against the methyl, ethyl, and hydrogen. When we reach the transition state, not only is the bond to oxygen forming and the one to bromine breaking, it's also when the ethyl, methyl, and hydrogen are on the same plane. When the new bond fully forms and old one breaks, the methyl, ethyl, and hydrogen won't remain on the same plane. They are pushed to new positions on the other side of the central carbon from their starting points. The product's butanol, and we can now determine the configuration. Because it has the highest atomic number, oxygen now has first priority. Next is again the ethyl group, but this is to the right, which means the configuration is R. This is conversion of configuration and comes with it a general principle we can apply to predicting the outcome of SN2 processes. S reactants yield R products, R reactants yield S products, and if we don't know the configuration of the reactant, we cannot determine the configuration of the product. If your head is spinning after all this, that's probably a sensible response, and that's why I'm stopping with this helpful trick. We've covered the absolute basics of nucleophilic substitution here, and there's plenty more to discuss about SN2 reactions, and don't forget about SN1 as well. Until I get to those videos though, thank you very much for watching this one, and if you have any comments or requests, please leave them below.